Hello everyone. This video I'm going to show the application of Newton's second law. Actually, there's a lot of problem, a lot of application for Newton's second law of motion. I just pick up some interesting one, and I'm not going to do all the application problem of Newton's second law. There's too many of them. And this one I feel very interesting. It's a roller coaster problem. And this problem is can be viewed as let me see, yeah, as this. And when your car going to a roller coaster doing a uniform circular motion, let's assume it's a uniform circular motion. Okay, for roller coaster, let's assume very simple one situation, roller coaster problem. And in a uniform circular motion, the radius is r. Okay, and the problem is like this: what's the minimum speed for the car reach to the top? Top means here. Okay. For this problem, maybe in this course, you will solve this maybe just by energy conservation. Energy conservation can solve this problem, but for this section, I just want to. We also can use Newton's second law to discuss the problem. Okay, so why there is a minimum speed for the car reach to top? Intuitively, yeah, I need more speed. I need a minimum speed to pass the top point. Okay, yeah, intuitively we need a minimum speed to pass the top point. But why is that? Why is that? So let's do some as analysis. When we use the force concept force, how do we analyze this problem? Um, we do analysis on the 2 points. One is bottom and one is on the top. Okay, and you will see bottom. You will see a difference. First, which point we okay, we start from the bottom. We start from the bottom. TTOM. Okay, at the bottom point, what force do we have? Where we have the weight, and we also have normal force from the track. Yeah, we have also for normal force from the track. Okay, and when you do the uniform circular motion, you will feel a centripetal acceleration point to the origin or center of the circle. So your at the bottom, your normal force must greater than your weight because it must be your normal force must be greater than weight, or you won't have any force to centripetal force to pull the car inside and make a change and change the direction and then do the uniform circular motion. So it must or you can or you can never do the centripetal uniform circular motion. Okay, and the centripetal acceleration, the formula is v squared over r. So we will have this n equal to normal force is r v squared over r plus g. Okay, that's for bottom. And for the top, okay, top is interesting. At the top, we have the weight. Okay, no problem. We also have the, sorry, let me turn the turn of the volume. And we also have normal force. At the top, we also have normal force. The normal force also point to the same direction. It only point to downward direction as the weight. And at the top, the centripetal acceleration, the direction of centripetal acceleration is also point to this. We should use that. At the top, the centripetal AC is also pointing to downward, so they have same direction. And this problem we use positive, upward positive, downward negative, and we will have this minus m minus mg equals to minus mr square. So we will have a normal force equal to, let me see, normal force and the square over r is minus g. Mm, mm, g mg rg. Oh, oh, let me see. Do I make this right? N equal to m minus m minus g. Okay. Hmm. Hmm. Okay. Okay. So that's okay. That's what we have. Okay. So why is the question as lately is there any minimum speed to pass to for a car to reach the top? Okay, because at the top when you see this picture at the top, even if in at the top, even if it even if your normal force equal to zero, you still makes turns. Still make turns. Okay, still make turn. Why? Because at the top you have the gravity, you have the weight. The weight also pulling you to the center, also pull the car to the weight provide the centripetal acceleration to help the car to make a turn. So even if at the top there is no normal force, you still make a turn. The weight will help you make a turn. Okay, but at the bottom, you must have normal force at the bottom. Bottom. You must have normal force at the bottom, but at the top, even if you don't have normal force, that's fine. That's fine because then the weight help you the car turn. So the normal force can be zero. So the normal force is when normal force is equal to zero. What does that mean? This will help you give you an equation. It can become zero equal to m v squared over r minus g. So just divided this, you will have the v squared equal to gr, right? And v is equal to square root of g times r. So this is our minimum speed. Minimum speed. This minimum speed gives the n0. Okay, gives the n0. That's a minimum speed. Okay, this is from force concept. It's from force second law point of view. Yeah, you will have a minimum speed. Okay, you have minimum speed to pass the point. But from energy conservation point, yeah, you need enough kinetic energy to overcome the potential energy. Initially you have kinetic energy. Okay, let's say this is V. Initially you have kinetic energy. Your kinetic energy must overcome the potential energy, right? That's from energy conservation, from energy point of view, and it's more intuitive. But we also can use from force perspective. From force perspective, we also can reach the same conclusion. So you need a minimum speed. You can have from force perspective you can have a minimum speed to reach the top. Okay, so at that point, weight can help you make a turn. Okay, so this roller coaster is a very simple, interesting problem. Okay, to me, it's an interesting problem. So that's a video to help you to do a little more understanding of Newton's second law. Yeah, this F equal ma. So I don't think I need to write it to make clear anymore. F equal ma, everyone knows that. So I don't have to need to write it one more time. Okay, so here this is a video, and see you in the other video. See you next time. Bye bye.